Hello mathematicians, we're now going to take a look at the rectangular hyperbola. And the rectangular hyperbola is just our usual hyperbola with the asymptotes at right angles to each other. Now if the asymptotes are at right angles to each other, that means that the asymptotes must be y plus or minus x, so that we can get this right angle in here. And in that case, we need a equal to b, because we know the equation for the asymptotes is going to be y equals plus or minus b on a times x. And if a equals b, then in our ordinary equation for the hyperbola, which we know is x on a squared minus y on b squared equals 1, then if a equals b, we've got x on a squared minus y, x squared on a squared minus y squared on a squared, multiply through by the a squared, and we get this equation for the rectangular hyperbola. So we know how this is linked to stuff that we already know. So again, we keep building up that chain of connections. Likewise, we take our eccentricity for the hyperbola, which is e squared is 1 plus b squared on a squared, and again b squared on a squared becomes 1, so e squared equals 2, or e equals root 2, which is, as we'd expect, greater than 1. So in this diagram here on the left, we can see the rectangular hyperbola, so just a special case of the ordinary hyperbola. But here on the right, we see that we've got the hyperbola looking perhaps more like you're familiar with it from the Year 11 course and maybe the junior school course as well. And that is with the hyperbolae branches sitting in quadrants. And in this case here, what's happened is that we've taken our rectangular hyperbola, rotated it through 45 degrees. So we refer to this as the rectangular hyperbola with the asymptotes used as the axes. And in that case, the equation for our rectangular hyperbola with the asymptotes used as axes becomes this. Again, more like the form that we're used to. So xy equals c squared, which is a squared on 2. And you might link that back to the equation that you would have used previously for the rectangular hyperbola, or for the hyperbola, sorry, which is y equals k on x. So we were really dealing in the Extension 1 course and the Advanced course with a particular case of the hyperbola. Now let's take a look at this on the GeoGebra. So here we've got our rectangular hyperbola. You can see the value of a here is 4.3. As I change the value of a, then I change how closely the hyperbola fits to the axes. So the equation for our hyperbola, x squared minus y squared equals a squared, 3.6 squared. Now if we plot the hyperbola with the asymptotes as the axes, you can see that we get that more familiar shape, and it is 2xy equals 3.6 squared, or in other words, xy is a squared on 2. And when we do switch the asymptotes to be the axes, the foci and the directrices of course switch as well. So if you notice the two foci, they are at the coordinates a and minus a, and the two directrices, although it doesn't have it marked on here as such, they are at y plus x equals plus or minus a. So you can see where the axis cuts through, or where the asymptote cuts through the axis is at plus 3.6 and minus 3.6 down here. Now if you like to reinforce for yourself why that is, if we imagined the location of the focus as AE0 and we rotated that around through 45 degrees, that distance, a root 2, has to be the same distance, but the new value of x and of y is A and A, just because of Pythagoras. And likewise for the directrices. They were the lines x equals A on E for the rectangular hyperbola. Then once we switched it around to have the asymptotes as axes, then that distance of A on root 2 has become the side of a triangle, right angle triangle, and the hypotenuse of that was now A. So we have these relationships for the foci and the directrices, and the asymptotes of our new triangle, hyperbola, are, as we have known for a long time, y equals 0 and x equals 0. So the rectangular hyperbola can also be defined in parametric form as x equals ct, y equals c on t, where again remember that c is equal to a on 2. So we'll just have a quick look at this on GeoGebra as well, and what we're going to see here is basically the parameter in action. So as I vary the value of t between -10 and +10, then if c is 2.85 and my coordinates are plotted as x equals ct, y equals c on t, then what I get is my hyperbola being traced out. I'll just let it run back. There we go. So that might hark back to the work on the parabola in parametric form that we looked at in extension 1. Now for these examples. First one, sketch this rectangular hyperbola showing all relevant features. So we know that if xy is 16, that's going to give us that a squared on 2 is 16, so we can get the value of a. And when we draw our hyperbola up, which of course doesn't cut through the axis, just my poor drawing, we've got our foci at AA, 4 root 2, 4 root 2, and also the negative of that. We've got our directrices at x plus y equals plus or minus a, and of course y equals minus x and y equals x are the axes of the asymptote when we draw it like this. And it's very easy to go from Cartesian to parametric form. Given that xy equals c squared, we can get c, so therefore x equals ct, y equals c on t. If we were given the equation in parametric form, we can of course also eliminate the parameter to get Cartesian form. So have a go at these in set 5.